recently come into that post. She was a visiting researcher at Princeton, and she has a PhD in statistics, PhD in electrical engineering, and a master's in statistics from Stanford in 2009. And she's also been a postdoc at Caltech. So her expertise is in information theory, and we're very pleased to have her present to us today. So please join us in welcome.
So thank you very much for the introduction, and thanks a lot for inviting me. So today I'm going to talk about data compression, compressed sensing algorithms, why they are important, what are the challenges in designing these algorithms, how these two problems are connected with each other. So we are living in a world where data generation rate is soaring every year. So I have a figure here that shows the estimated amount of data that has been created in the world during past few years, and also its estimated value for the years to come. It also shows the amount of storage that is available. So the red curve shows the amount of storage. And as you can see, we have already surpassed the amount of storage that we have, and we have to throw away some of the information that we are collecting. And as time goes on, the situation only gets worse, and the gap becomes larger and larger. So where is this data coming from? It comes from various sources. It comes from social media like Facebook, Twitter, and so on. It comes from financial markets, environmental sensors, healthcare data, genomic data, and so on and so forth. So we have these massive data sources that are diverse, and we would like to perform various kinds of actions on these data sources. We would like to acquire them, store them, communicate them with other users, sometimes remove noise from them, sometimes perform prediction, like in the case of financial markets. And we would like to perform all these actions efficiently. So we would like algorithms that are efficient. And by efficient, I mean they have low computational complexity, and you can implement them. And also, we would like to have algorithms that adapt to various data types. So these data are coming from various sources. They have different kinds of structure. Their structure changes over time. So we don't want to design specific algorithm for each kind of data that we encounter. We would like algorithms that are applicable to various data sources. And this topic of diversity in the data has been studied in information theory under the title of universal algorithm. So an algorithm is called universal if it's not designed for a specific data distribution, data structure, and so on. But still, it achieves the optimum performance without having this knowledge about the structure of the data. So it's not obvious that such algorithms even exist that can get to the optimal point without knowing the source distribution. But people have proved in some cases, like case of data compression, denoising, and prediction, such algorithms exist, such universal algorithms that get to the optimal performance without knowing the source distribution. And a very successful story in this area is the case of universal lossless compression. So in this area, we have a LZ algorithm, Lambda-Ziff algorithm, which is a data compression scheme, which is very efficient. So it theoretically achieves the optimal performance, but its computational, the computational complexity of implementing this algorithm is very low. So that's why it has been implemented in many commercial products. So if compress, GIF, TIFF, all of these are examples of the schemes that we use every day, and they use this algorithm inside them. So in this talk, I'll focus on two specific kinds of functions that we do over, we perform over data. Specifically, I'll talk about data acquisition and data compression. And I'll talk about universal schemes in each of these problems. So let's start by the problem of data acquisition. So data acquisition is about acquiring or measuring a real valued signal. So it's real world signal. So we have a signal that's an image, a radar signal, a radio wave signal, and so on. And we want to capture this signal. And it turns out many acquisition systems, not all of them, but many of them, we can model them in this form. We can model the signal as a signal that lies in our N. So we have x that we want to capture. It's a signal in real value that has n dimensions. N is usually very large. And the acquisition system itself, we can model it in this form. So it's a linear system. What we observe is AX plus some measurement noise. A is a measurement matrix. It has D rows and columns. And W is the measurement noise in the system, which is always present. And from these measurements, from these noisy measurements, we would like to estimate our signal X. In order to be able to do this in the classical setting, so we have n unknowns, we need at least n equations, and we need more because we have noise. So we need to take number of measurements to be larger than ambient dimension n. But it turns out this to be very challenging because n is very large, and in many practical situations, getting these many measurements can take a lot of time. It's expensive. Storing these many measurements can be costly. So a very good example is the case of MRI machines. So in MRI, the person has to stay in the machine for like 20 minutes or more to let the machine get all the samples that it needs so that later on it can give us a reliable reconstruction of the data. And this happens in other applications like high-resolution imaging and so on. And it's, for instance, in the case of MRI, it's very challenging because it's, first of all, this makes the whole process very expensive, and also it's challenging, if, for instance, to ask a kid to stay calm inside the machine for that long. So what we desire to have is to reduce the acquisition time. It means that to get lower number of measurements. So we want to make D, the number of measurements, to be much smaller than the ambient dimension. But if we do so, what we get an underdetermined set of linear equations. And in general, it's not solvable. We can't get back our signal. But what people observed was that if we reduce the acquisition time, but still we have some knowledge about the structure of the signal, still we can get back, we can solve this underdetermined set of equations and get back our signal. And this is studied in the area of compressed sensing. It's relatively new, and people have proved that this is possible. So in a nutshell, a compressed sensing system would look like this. We have a structured signal. It has a low complexity signal. We perform some linear measurements. And from those measurements that are underdetermined set of measurements, we build a recovery algorithm that is designed based on our knowledge about the structure of the signal that gives us back the signal. Now, in many applications, we don't know exactly what kinds of structure are there in the signal. And also the structure of the data might change over time, and we might have some estimate, like if we know this kind of structure might be present in the data, but we don't know all the kinds of structures that are there, and also, as I said, it can vary over time. So it's desired to have universal algorithms that can recover signals from underdetermined set of measurements without knowing the underlying structure. So what we did was we designed the first universal signal recovery algorithm. So we formulated this problem and proposed this minimum complexity pursuit scheme. So what it does is it's based on Occam's razor. So among all this, so this is for the noiseless case, but for the noiseless case, what it does, among all the solutions of AX equal Y, all the signals that satisfy the measurement constraints, it looks for the one that has, it's the simplest. It has the lowest complexity. So this measure, which I'll define rigorously during the talk, measures the complexity of real valued signals. And we proved that this is a universal signal recovery scheme, and a signal which has complexity kappa, we can recover it from kappa log n measurement. So I should define what does it mean for an analog signal to have complexity kappa. But these are things we define rigorously and prove that these many measurements is enough. Another problem I'm going to talk about today is the problem of universal compression. So data compression is about efficient representation of the data. So now the signal has been captured, and we want to use as few number of bits as possible to store that data in the memory of our computers. And we have two types of compression schemes. We can have lossless compression schemes, the kinds of schemes you would use to compress text files. When you compress your report, later on when you recover it, you don't expect any errors in the retrieved file. So this is lossless compression, and we can have lossy compression as well. So this is the kind of compression scheme that we apply in compressing multimedia signals like images, audio, and video. So in that case, sometimes we can have some distortion, and either our eyes or ears can detect that errors, or they can detect, but we are willing to compromise because we have some constraints on the communication, the storage, and so on. So the basic idea in compression, the underlying idea in compression was, again, to use our knowledge about the structure of the data. We know the structure of the data, and based on that, we designed good compression codes. But again, the challenge I mentioned, the source model is not known and it varies over time. So it's desired to have universal data compression schemes. And existence of such schemes is already known, both for the case of lossy and lossless compression. And it has been known for a while that such schemes exist. For the case of lossless compression, where we want perfect reconstruction, in fact, there are a number of algorithms that achieve the optimal performance. They are practical, and that's why they have been used in many commercial products that we use, like LEMPLZ, adaptive arithmetic coding, context reweighting, and so on. But the situation is very different for the case of universal lossy compression. So people have tried hard to come up with universal algorithms for lossy compression that are efficient, you can implement them, but still achieve the optimal performance. They tried to extend these schemes, for instance, to the case of lossy compression, but they haven't been successful. So I have listed some papers here. These algorithms, if you look at them, they are either suboptimal, provably suboptimal, or they have huge computational complexity. So what we did was we designed two efficient lossy compression codes. One of them is based on tools from statistical physics, MCMC, and simulated annealing, and the other one is based on the Viterbi algorithm. And for the sake of time, I'll only review one of these schemes today. But both of them, in the limit of large block lengths, achieve the optimal performance. And our simulation results show that if you apply them to finite block length signals with finite number of iterations, still you get good performance. So this is one simulation results. I have a Markov source. These are upper and lower bounds on the rate distortion curve, and these are what we get from this algorithm, from the second one. So I gave you an overview of the kinds of problems I'm looking at and I'll talk about today. So now let's get more into the details of each problem and about the specific results we have in each area. So as I mentioned, many acquisition systems can be modeled in this form. So we have X that is in Rn, we perform linear measurements. What we observe is AX plus some measurement noise. And from these, we want to estimate our signal X. Again, I mentioned the classical setting. We need the number of measurements to be larger than n. But what is desired is to make D much smaller than n. So as soon as we reduce the number of measurements, so what happens is that we have a now fat measurement matrix. So D is smaller than n, so A looks like this. And we have the system of equations has infinitely many solutions. So it's not solvable. But the question is, what if we have some prior knowledge about this signal X? For instance, assume that we know the signal is sparse. The only thing we know about the signal is that the number of non-zero coefficients in this signal is bounded. So it has some non-zero coefficients, k non-zero coefficients, and the rest are zero. And this is a very relevant assumption. I mean, it's not just for coming up with theory. This happens in many practical cases. The signals are sparse in some domain, like time, frequency, wavelet domain. In some domain, they are sparse. They have some large coefficients. The rest are not exactly zero. They are very, very small. So we can apply these models to them. Now that we have some extra knowledge, so we have a system of equations that has infinitely many solutions, but we know the signal is sparse. So if we apply our knowledge, we can come up with this algorithm. We look for the solution that is sparsest among all the solutions of this set of equations. And if we do so, then then we can prove that, in fact, if you take only 2K measurements, then we can have a measurement matrix A for which this algorithm returns all K-sparse signals exactly with no error. So it's under determined set of equations, but we can recover our signal exactly. And if K is smaller than N, much smaller than N, this tells us the number of measurements we need is much smaller than N. We don't need to go to all high dimensions. Of course, this is not a practical scheme. It's not implementable, but practical schemes exist. That's what people study in compressed sensing. They have come up with very efficient algorithms that approximate or sometimes find the solution of this exactly. So this was based on looking at one specific kind of structure, basically looking at sparsity in the signal. So the signals we have various kinds of structure, and that's what people have looked at. So people have looked at group sparsity, low-rank matrices, model-based compressed sensing, signals that defined in terms of atomic norm, and so on. So for each of these problems, if you look at them, we have a structured low-complexity signal, and we have a recovery algorithm that is designed based on our knowledge about a specific kind of structure that is present in the data. We know it's a low-rank matrix. We know it's a sparse signal, group sparse signal. So based on that knowledge, specific knowledge, we come up with a recovery algorithm that recovers those kinds of signals from an underdetermined set of equations. But again, this is not so in practice, for many signals, we don't know what kinds of structures are there in the signal. We might know it's sparse, but it has many other kinds of structure present in the data. And if we exploit all those information, we can further reduce the number of measurements we need. And also, as I said, structure times varies over time, so we need algorithms that adapt to this. So we need universal signal recovery algorithms. And to design such algorithms, we need a measure of complexity. So what does it mean for a signal to be low complexity? How can we differentiate like sparse, low rank, all these from the signals that don't have any kind of structure? So we need a measure of complexity. And after finding such measure, then we can come up with a universal signal recovery algorithm. So in compressed sensing, most of the cases people deal with, we model the signal by deterministic signal. It doesn't come from a probabilistic distribution. And measuring the complexity of deterministic signals has been studied in this algorithmic complexity theory. So an algorithmic complexity of an object, it's its intrinsic descriptive complexity. So it's a complicated term, but let me define it through an example. So assume that I have 3 binary sequences. One of them is all zeros. The other one is 0, 1, 0, 1, 0, 1. And I have a random sequence. This random sequence is generated by a Bernoulli half process. So it doesn't have any structure. Now if I ask which of these sequences are simple and which ones are complicated, I think all of us agree that the first 2 sequences are simple and the last one is complicated. Is a complex sequence. And the intuition behind our reasoning is that the first 2 sequences are simple to describe. If I want to specify them, it's simple. And the last one, it's hard to specify. I mean, I should specify every position in this long sequence to specify the whole sequence. There is nothing a short sentence that can describe this sequence. And this intuition has been captured in concept of algorithmic complexity, and it's so basically people define Kolmogorov complexity based on this nice intuition. This concept was introduced by Solomonov in 1960 and Kolmogorov in 1965. And as I said, it measures the intrinsic descriptive complexity. So how is it defined more rigorously? So assume that I have a computer, a universal computer, but for the sake of now, you assume it's a normal computer that we use every day. This computer gets a program and generates an output. So I give a program is just some bits, 0, 1s. And for this input, it gives me an output. Now I can define the complexity of sequence X with respect to this computer in this one. So for me, so assume that X is also binary. So I can say the complexity, we define the complexity of X with respect to this. as the length of the shortest program that generates X. So I can have various programs. I can write different codes that generate a specific sequence. So I have different codes, and I look at them. And you look for the one that has the shortest length. The length of that program will be the Kolmogorov complexity of X. So why is it a good notion? So let's look at some examples. For instance, the case of all zeros. So I have a sequence all zeros, and I want a code for specifying this. So and assume that I know the length. So then it's very easy. It's just the code is print out these many zeros. It's a very finite length code. The length doesn't depend on n. So the Kolmogorov complexity of X given n is bounded by some constant c that doesn't grow by n. So that matches by our intuition that this is a simple sequence. Another example is I have a string of length n, and it has k number of non-zeros. So what is now the complexity of this? So now I need a code to generate this. One possible code is I ask the code to generate all such sequences. So I have n choose k such sequences. After the list, so this is easy. It's a short that can generate all these. Now I should specify which one in this long list is my specific sequence. So since I have these many sequences, log of this number will give me an upper bound on the Kolmogorov complexity of X. And now, unlike before, if k is proportional to n, this quantity can grow with n as well, and these sequences are potentially complex. And if I have a random sequence, so it's totally random, it's Bernoulli half. Now if I look at 1 over n, the Kolmogorov complexity of xn, this converges to 1 in probability. So such sequences have complexity of order n, close to n. So these are highly complex sequences. So now, so we have this notion of complexity for deterministic signals. But compressed sensing, so this was for binary or finite alphabet sequences, but compressed sensing is about real valued signals. And Kolmogorov complexity of a real valued signal is infinite. So we can't directly use this notion to capture the complexity of signals or differentiate between simple or complex signals. One potential solution is to consider signals that only consider signals that have finite computational complexity. So this has been explored in this paper. What happens is that the problem with this is that the class of signals that have finite complexity is very limited. It doesn't cover any of the classes we care about. Doesn't K-sparse signals, low-rank matrices, almost all of them have infinite Kolmogorov complexity. So this is a very limited result. So the approach we take is that, so we quantize the signal, we look at the Kolmogorov complexity of the quantized signal. This again grows to infinity, so it doesn't tell us if the signal is complex or not, but we normalize it by the quantization level and get an object that we can show is a good measure of complexity for such signals. So let me define it more rigorously. So assume that I have a signal x, and for now assume that the values of x are between 0 and 1. It can be easily extended to arbitrary ranges, but for now assume that x has the values of x are real, but between 0 and 1. And each component in x has a binary expansion. So these are zeros and ones, and we define m-bit approximation of xi in this form. So I take the first m bits in this binary expansion, the first m important bits. Now, we define the complexity of xn at resolution m when I quantize every element in x in m bits, concatenate them, get a sequence of length mn, and look at the complexity of this long sequence. Now, what we define Kolmogorov information dimension, or KID, is looking at this complexity at resolution m and normalizing it by m, the quantization level, the number of bits I'm taking in each binary expansion. So why is it useful? So this was the definition. So we can prove that for structured signals, this KID is much smaller than n. So we expected it to be smaller than n. Remember, for random signals, this is n, the Kolmogorov complexity. If I have, we can prove that if I have a signal that has KID less than kappa, then I can recover it from kappa log n measurements without knowing the underlying distribution or structure. And for unstructured signals, we can prove KID is of order n. So let's look at some examples. As I mentioned, for if I have a totally random, which is uniform between 0 and 1 over n, the KID of xn goes to 1. And this is directly follows from the previous result I mentioned for binary sequences. Now I have quantized them. I get Bernoulli half sequences. So this is basically corollary of that result. Now, class of structured signals, k-sparse signal. So this is the class I mentioned earlier. I have a signal of length n, and it has k non-zero elements. Now we can prove KID of such signals is upper bounded by this expression, k plus k log n over n. And if k is smaller than n, the KID is much smaller than n. And we can use this result to other instances. We can apply, I mean, I'm not giving the equations here, but we can apply it to low rank matrices, piecewise smooth functions, sample of polynomials, and so on. And for each case, we can bound the KID and show that it's a good measure of complexity and how it measures the structure of the signal. Now that we have this measure of complexity, we can build a universal recovery algorithm. So this was our setup. We have a signal in this form. We perform linear measurements. So for now, I assume that measurements are noiseless. So what I get is y, which is AX. A, the measurement matrix, we build it in this form. So the terms are IID with Gaussian distribution. And I take the number of measurements. Now, to recover my signal x, I look at the Kolmogorov complexity at resolution m of x among all, and try to find this among all the infinitely many solutions of Ax equal y, the one that has lowest complexity. So now, in order to specify the performance of this algorithm, so how does MCP perform? To specify this, I need to tell you how many measurements should you take. I mean, how many measurements do we need to have a reliable construction? How should we choose the quantization level? Again, that's a parameter. And also, what is the error? What's the error we get from this algorithm? So the result we have an upper bound on the error for any choice of m, n, and d. So it's a finite dimensional analysis. It tells you if you take these many measurements, choose the quantization level in this form, what's the error you'll get, what's the probability you exceed that error, and so on. So the expression is complicated. I'll tell you more about a simpler result that basically a corollary of that result, where we take m to be log n. So we choose m to grow as log n. Kappa n is KID when I choose m to be log n, and take the number of measurements to be kappa at this resolution times log n. So it's kappa log n. So what happens? So in that case, we can prove that the probability that error exceeds any epsilon goes to 0. So basically, this algorithm recovers any signal with complexity kappa from kappa log n measurements. And the error is, you can make it as small as you want. And we have this bounds on how this error is falling off and everything. Now let's look at an application like the class of sparse signals. I showed that we have this bound for any choice of m. We have this bound on the KID. Now we can plug in m equal log n. So log n and log n cancel out. I get 2k plus something, which is very negligible. So it tells me that if I take 2k plus 1 log n measurements, this algorithm, the probability that its error exceeds any epsilon positive goes to 0. And we can, again, as I mentioned, we can apply this to various classes, and for each one derive how many measurements do we need to have a reliable reconstruction. So I focus on lossless, noiseless measurements, where the measurements are perfect, but in practice we have noise in the system. So what we measure is AX plus some W, and W is usually modeled by IID Gaussian distribution. So sigma squared is the variance of the noise. So now that we have noise in the system, we need to update our algorithm. We need to take into account that the measurements are noisy, and we update MCP, we drive noisy MCP, which looks like this. So now we look at all the signals up to certain complexity and look for the one that best matches our measurements. So minimize ax minus y squared, del2 norm subject to this complexity constraint. And again, we have this result on the performance, which tells us if I take m as log n and take these many measurements. So before we had kappa and log n, now I have 8 gamma times kappa and log n. So if I take these many measurements, the probability that my error exceeds this constant times sigma squared, the variance of noise, goes to 0. And this gamma here basically determines a trade-off. As I take more and more measurements, the error becomes smaller and smaller. So it shows here, and here I have rho, which is function of gamma. Now, to give you a sense of how this result works, if I take gamma equal 4, it tells me that I take 32 kappa and log n. The probability that the error exceeds sigma squared over 8 is small. And then something I want to emphasize that this result is giving me an error of order of the error of the power of order of the same order as the power of the noise. So I'm seeing a constant times sigma squared here. So just to give you an idea about the proof in just one slide. So this was our setup. We performed linear measurement, noisy linear measurements, and minimized the measurement noise subject to complexity constraint. So our original signal also satisfies the complexity constraint. So it satisfies this constraint. So our reconstruction should have a smaller error compared to the original signal. So we look at this and compare the error of xo with x hat o. And if I look at the error of xo and plug it in here, I have axo minus yo, which is just w. So I get w here, and here yo I can insert axo plus w. I do some algebra, I don't want to go over it. It's just simple algebra, I get this expression. So this is the basic. So we start the proof from here, that we have this expression. Now we want to work on with this expression and get a bound on the error. What is the error? It's this distance between xo and x hat o. So the proof bounding this distance has various components. Some of them are standard techniques, like tools from random matrix theory, concentration of measure, and so on. But some of them are specific tools that are for this specific problem, using Kolmogorov complexity, counting how many low complexity signals are there, and so on. So I talked about MCP. It's a universal compressed sensing algorithm. It's robust to noise. I here showed the Gaussian noise, but we can prove it's also robust to model mismatch and so on. But it's not practical. You can't implement this algorithm. It's just a theoretical algorithm that proves universal schemes exist for signal recovery. So what we are working on right now is developing practical recovery algorithms. So there has been some initial work in this direction. People have used MCMC methods and so on. These are some empirical results, and they have got some encouraging simulations in this direction. But we are now working on developing algorithms that are motivated by theory, that achieve optimal performance, and are practical. And in going towards that direction, we have established the connection between compressed sensing and data compression. So these are two different problems, but I'll talk about it in one slide, how these two are in fact connected and how we can use data compression schemes for compressed sensing algorithms. So another problem I mentioned at the beginning was the problem of universal compression. So this graph here shows the basic setup in a compression scheme. We have a signal that we want to compress, and this signal is usually modeled by a stochastic process. So it has a probability distribution. And so far I was talking about acquiring data acquisition, which was about real valued signals. In data compression, I focus on finite alphabet signals. So they come from, they can take on only a finite number of values. We have an encoder. It observes n source symbols and maps them into nr bits. And then the decoder, it's basically a lookup table. Every nr bits, it maps it into a reconstruction sequence x hat n. So the performance of such schemes is measured in terms of rate. How many bits are we spending per source symbol? And also its reconstruction quality. We can have lossless, as I mentioned. We want xn and x hat n to agree always or with very small probability, with very small probability of error, or we can have lossy compression. In lossy compression, we measure the distortion of the code in this form. So it's an average, expected average per letter distortion defined in this form. And clearly there's a trade-off. As you increase the rate, you get better performance. And every source has its own rate distortion curve. So it's something characterized in information theory. And the characteristics that comes from what source distribution are you using. So now the basic idea in information, in data compression, as I mentioned, is modeling the source. So we model the source by the stochastic process. For instance, I have Bernoulli source. I model it by I have binary source, and I model it by Bernoulli 0.1 source, meaning that I expect 10% of my output bits to be 1, the rest to be 0. Now if I use this model, it turns out the probability that my output sequence does not comply with this model is exponentially small. So we can compute this. So what does it mean? For instance, in this example, the probability that the percentage of ones at the output deviates from 0.1 is exponentially small. So it tells us it's enough to code efficiently, if I'm under this model, it's enough to code efficiently those typical sequences. So how many typical sequences are there? We can prove that the number of typical sequences over all sequences is exponentially small. So this tells us how we can get an efficient scheme for data compression. And this intuition holds for lossless and lossy. So we have a small set inside the set of all sequences that we need to care about, and for the rest we can either throw them away or have an inefficient scheme and still achieve the optimal performance. So as I mentioned, this is the source model is not known in practice. In many situations, we don't know the data generation mechanism. So we don't know what's the exact model of the source, and the model changes over time. So we have different kinds of data at different times. So what is desired is to have a universal data compression scheme. So what does it mean? We need family of algorithms that for alpha positive minimize R plus alpha D for all sources. So existence of such schemes is already known. We know such schemes exist, but for the case of lossy compression, there was no implementable universal lossy algorithm. So as I said, we know such schemes exist, and there are various algorithms with huge computational complexity that can achieve this. One of them looks like this. So in order to code sequence xn, I look for sequence x hat n, which minimizes this cost. What is this cost? It has two terms. So remember, I want to minimize R plus alpha D, and that's alpha. I'm not sure if I mentioned. Alpha determines which point on this curve I want to operate. So it's a parameter of the system. So for every xn, I look for the sequence x hat n, which minimizes this. It has f of yn, which measures the compressibility of sequence yn. It's a measure of rate, basically, and also the distance between xn and yn. So it's R plus alpha D, basically. And f should be a valid measure of compressibility. I won't go into the details of how to build these measures. But for choosing various kinds of f, people have proved, and we did too, that this algorithm achieves the optimal performance as the block lengths become larger and larger. But this is not a practical scheme. It has huge, exponentially large computational complexity. If you have binary sequence, it has 2 to the n possible reconstructions, and you should go over all of them and find the one that has the lowest cost. So in order to find the minimizer of this cost, we look at one specific function f. So we look at hk of yn, which is conditional empirical entropy. It's a valid measure of compressibility, and it's defined in terms of m of yn, which is k plus 1's order empirical distribution. So let me define it through an example. So assume that I have binary source, alphabet 0, 1, k is 2. Then m of yn will be a matrix of 2 by 4. Every row in this matrix corresponds to one of the symbols in the alphabet. So here, one of them corresponds to 0, this one corresponds, the second row corresponds to 1, and every column corresponds to a sequence k-tuple of a binary k-tuple. So I have 0, 0, 0, 1, 1, 0, 1, 1. Now, every element in this matrix counts how many times a specific pattern has appeared in this yn sequence, and then normalizes it by n. So again, by an through an example, if I have yn in this form and it has length 20, and I want to measure m0, 0, 0, I count how many times this pattern has appeared in the sequence. So in this example, it's 3 times. I count them 3, and then normalize it by the block length 20. And so this has positive terms, and they add up to 1. So it's basically a probability distribution, but it's an empirical probability distribution. And in terms of this matrix, we define case order empirical entropy in this form. So it's a maybe complicated formula, but what it does is looks at so every column, as I said, has 2 rows, 0 and 1. It looks at each column and looks at the entropy of that column. So if I normalize it, becomes a probability distribution every column, measures the complexity entropy of that column, and then takes a weighted average among all the columns. And it, as I said, this is a valid measure of complexity. But to give you an intuition, for instance, if I have binary source, and k is 2, and this is the block length, and I have Bernoulli half process, then if I run a MATLAB code and look at the output, and if you do this with high probability, you'll get 1. So this is not a compressible signal, and what I get is 1. And if I run it on a different source, like Bernoulli 0.1 source, which is compressible, the number I got was this one, 0.08, which is much smaller than 1. So it's compressible signal, HK of yn is smaller than 1. Now I go back to the exhaustive search scheme. Now I have insert HK of yn here. Still it's challenging. It's not clear how to find the optimizer. And as I defined in the previous slide, HK of yn is a function of m, empirical distribution. And this function is highly nonlinear, as you saw in the previous slide, but we can prove it's concave in M, which turns out to be important. So now what we do is we take a first order approximation of this function g around some point m star. So if you just look at the first order Taylor expansion of g. Now I can come up with I can think of another algorithm. Then instead of this original cost, I look at this linearized cost. So I insert this here and derive another algorithm. So why are we interested in doing so? Let's call lambda to denote the coefficients when I take the partial derivatives of g with respect to m. So this is the algorithm we have. And if we do some simple algebra, what we get is this form. So we wanted to minimize this cost. So this was the linear approximation. I inserted it here, and this is the cost I get. So what I do here, I do some simple playing around with the terms, and I can rewrite the cost in this form. It's a summation from 1 to n. Now, what happens now, I'm sliding over my yn sequence with a window of length k plus 1, going step by step further, and assigning different costs to different windows of length k plus 1. Now we want to minimize this. And it turns out this is sliding over the signal and assigning costs to various different contexts. In fact, it's equivalent to finding a minimum weight path in a trellis diagram. So we can form a trellis diagram. Unfortunately, I won't have time to go into the details of how we build this, but it has 2 to the k number of states corresponding to various contexts we encounter, and the value we see at the time I will determine how we transition between the states. So we want to find a minimum weight path in this trellis. Now this is a standard problem. We know how to solve it. We have the Viterbi algorithm, which is a dynamic programming, and it's very efficient, and we can use it and find the minimizer of this cost, which is basically finding the minimum weight path in the trellis. So the question is, so how well is it doing? It's just some linear approximation around some point m star. So how good is it? it's efficient, we can find a minimizer easy, but is it good? So it turns out we can prove that there exists some MS star for which if we do the approximation around that point, then that both problems have the same set of minimizers, and basically the same performance. So the challenge is now finding that MS star. If you find it, then we are done. We can run Viterbi algorithm and find a minimizer. Now, what we can prove about MS star is that we can prove that it's in fact the empirical distribution of x hat and the solution of the original problem. We can also find a non-convex optimization problem whose solution will give us the MS star. But so these are not directions that we want to pursue in finding MS star. We can do this numerically, but instead of doing this, we use the properties of MS star that we learned from these two and propose an iterative algorithm. So the algorithm at each time it makes, so it starts from an estimate of MS star, and at each step it makes the approximation better and better. And we can prove that after a finite number of iterations, the algorithm stops, so it doesn't go forever. So this is an example that I showed before. So I have binary Markov source. This is the transition probability. This is the block length. And these are upper and lower bounds on the rate distortion curve. And this is the performance of the code. And you can see how it can get very close to the curve. And it doesn't, as I described it, doesn't know anything about the source distribution. And this curve here, this figure here shows how many iterations do we need. How many times do we need to run the Viterbi algorithm? So the horizontal axis here, it's alpha, which corresponds to different points on the curve. So as you can see, the number of iterations is not that much. In all cases, the average is below 15. So with a few number of iterations, the algorithm converges and finds and stops. So I talked about these two problems. I talked about universal compressed sensing and universal compression. Now, one question is there any connection between these two problems? And the reason we are interested in establishing this connection is twofold. First of all, as I mentioned, people in compressed sensing have looked at different structures in data acquisition. They have looked at sparsity, group sparsity. Basically, they have looked at simple kinds of structure. But the kinds of structure we use in data compression are far more complicated. And if we can use data compression codes for compressed sensing purposes, like the kind of codes we have for image processing, we have compression codes for image processing. So imagine that we apply them in compressed sensing. They can potentially reduce the acquisition time much more and give us much better performance. Another reason we are interested in this direction is that I told you about this universal compressed sensing scheme and how it can recovers the signals, structured signals from another determined set of equations, but this algorithm is not practical. And in order to make it practical, if we establish this connection, hopefully we can use tools and techniques we have in universal lossy compression and apply them in building universal data acquisition techniques. So in fact, we proved recently that there is a connection. There's a nice connection between these two. So I don't have much time to describe it into details, but to give you a flavor, assume that I have a code set Q. You can think of Q as the set of images. And I have a code for this set. So it has rate R and distortion D. And I perform linear measurements over this set. So I perform D number of linear measurements. Then what I want to do is I want to recover my signal back without knowing anything else about the signal other than we have this compression code for this set of signals. So we can prove with fact it's possible to do so. So if you take these many measurements, so it's a function of rate distortion function R and D, or basically R over log of D, then and you take the reconstruction in this form. So look at the code words of this code and find the one that best matches your measurements. Then the probability that your error exceeds this value, which is again depends on distortion, is exponentially small. So you can least in principle, we can use data compression schemes for compressed sensing algorithms. So I talked about, so to wrap up, I talked about universal signal recovery algorithms, designing efficient, how we formulate this problem and we prove existence of such schemes. I talked about designing efficient universal lossy compression schemes, and how these two problems, at the end I mentioned how these two problems are connected with each other. Thank you. Yes.
Are you talking about the minimum complexity for one set of data, or over time, or I wasn't quite sure?
Yes, for one set of data. So you have a data that you have done some linear measurements, and from those linear measurements, you want the simplest data that match those measurements. Does it answer?
Essentially, you're defining an order for the subscripts of X, and then saying which one you're thinking the solution is.
Oh, you mean x1, x2, x3?
Yeah, which X's you're going to fit.
Oh, this is the whole complexity of the whole vector. So it's, for instance, it's an image. So this model, like you can think of it as an image that I have. So x1 is pixel 1, pixel 2, pixel 3. So there is no ordering.
So it would be.
I mean, there is an ordering. I mean, but it's inherent in the problem. Inherently, we have an. Very good question. Yeah, in fact, there is a connection. For instance, if I have an IID process that comes from certain probability distribution, then we can prove. So in finite regime, it's not clear how to connect them because one of them is hard to compute. But we can have bounds. But in the limit, there is a nice connection. If I have a source which is IID, comes from probability distribution, 1 over n Kolmogorov complexity of xn, we can prove it converges to the entropy of that process. So these are, in fact, nicely related in the limits.
Okay, well, thank you very much.
Thank you.